Don't you hate getting to campus and spending hours trying to find a parking spot? This not only wastes everyone's time, but it also increases the amount of pollution in the air. Lucky for you, we have a solution. Presenting the Parking Occupancy Monitor by RetroPark. The Parking Occupancy Monitor, also known as the POM, tracks parking lot occupancy in real time to a high degree of accuracy in flat lots using machine learning. Current occupancy solutions either rely on controlled entrances and exits or sensors placed in each individual spot, which is either impractical or results in a higher final cost. This product is being brought to you by the following engineers.
Hi, my name is Patrick Kavanaugh, and I am a computer engineer and I'm the lead designer of the Parking Occupancy Monitor. My skills include Python, C, C++, Verilog, CAD, soldering, and 3D printing.
Hi, my name is Giselle Contreras Velarde. I am an electrical engineer and I am the project administrator. My skills include Python, C, soldering, Eagle, and PSpice.
Hi, my name is Will Sanchez. I am a computer engineer and am the project technician. My skills include C++, Verilog, Python, soldering, circuit analysis, and design. The POM is composed of a high-quality 13-megapixel camera with a custom integrated IR filter alongside a Pelco IR flash that works together to track parking spot occupancy at all times of the day. They are assisted by a retroreflective target placed in each parking spot, which increases the device's accuracy, especially at night. The POM utilizes a Raspberry Pi 4B to run the image data collection, image processing, and finally, the series of neural networks used to detect the occupancy of each individual spot. The following block diagram perfectly sums up the layout of the components within the POM and how it interacts with the environment. Here, you can see how the POM takes an image of the parking lot, processes it, and then sends it over to the cloud-based central server to then be displayed to a user front-end web page. This web page is accessible by multiple users at once and by any device capable of an internet connection.
The video you're about to see is a live demonstration of the Parking Occupancy Monitor in action. Grab your snacks and enjoy! Welcome to the RetroPark live demo. Right now we have the subscale model in front of us here with Hot Wheels cars acting as real cars, filling the Jimenez flat parking lot. On the left over here, we're gonna have my laptop. This is acting as the brains of the POM currently. And then we have up over here is the camera that we're using to stand in for the Pi camera that's actually going to be used on the device. As you can see here, we have cars filling up the parking spots. Each spot has a little retroreflective cross in it. There are a few spots that don't have it to demonstrate that it's able to work without them, but the retroreflective cross helps a ton with detection, especially at nighttime. So if you see here, you can actually see that it's currently running through and checking the occupancy of every single spot. You can see the number of the spot here, its occupancy or not occupancy, the confidence, and then the more important one there is the tug. And as soon as it runs all the way down to the last one, it'll send it over to the cloud server, and that will update it on the website. So now, if I wanted to, I could move some cars around, just place them to my heart's desire. There we go, it took the photo, and now it's going back through and checking the occupancy of every spot. As it is right now, it takes about a little under a second for it to run the spot through all three of the convolutional networks, the quorum, and get a response from it. So you can see here it sent it, and based on the web page, we've got a response from it. As you can see, it was able to detect the car in the top line. It was able to detect the two cars next to the parking, or the light pole there. You can see the yellow is the light pole. It was not entirely sure on the Cybertruck here. It's more sure that it's occupied than not, so that's reflected there with the little light gray. Same with the red car over there. It's not too sure, but it's sure enough that it's willing to say that it's occupied. And then it's quite sure with the bottom row here. So thank you for watching our demo. We hope to see you at the actual tech symposium with the fully built unit. The accuracy should be even greater, and we'd love to see you there. The overall flow of the software that makes the POM actually work can be broken down into 4 separate pieces. First off, it takes a photo of the parking lot. and then processes that photo into individual spot images, and then uses those images to detect the occupancy per spot and save that occupancy data to a file. Finally, it sends that data file to the cloud-based front-end server, which then displays it to the web page, accessible by anybody with an internet-capable device. The image cutter system is responsible for taking that initial photo of the parking lot and processing it into the individual parking spot images. This allows the neural networks to not have to worry about the entire parking lot and instead worry about individual parking lots. The next step in the software flow is really the bread and butter of the parking occupancy monitor. By utilizing a series of 3 TensorFlow convolutional neural networks, we're able to determine the vacancy status of each individual parking spot to an incredibly high accuracy. These neural networks are referred to as personas. That is, they each have a different personal way of detecting if a car is present in the spot or not. The first persona looks at the raw grayscale image. We call him Tom. The second persona first applies a canny edge detection filter to the image and then evaluates it. We call him Jerry. Finally, the third persona applies a Sobel XY edge detection filter to the image and then evaluates it. We call her Tweety. Each image is then passed through a quorum. That is, we ask each persona what they think the occupancy status of the spot is. The final step in the software flow that the POM handles is sending the occupancy data to the cloud-based central server. This central server autonomously receives this file and is then able to update the data displayed on the front-end web server seamlessly.
Like any senior design project, we ran into a few issues throughout the development of the product. Since our project heavily relies on infrared, we encountered a big issue when testing it against the largest source of infrared light, the sun. Although we were able to see our retroreflective targets, the light they were reflecting was not great enough to stand out from the background image. In order to fix this issue, we swapped our retroreflectors with retroreflective targets. These targets were X-shaped particle boards covered in retroreflective tape that ensured the target stood out compared to its surroundings.
The next issue we encountered was with our initial plan to place a POM on top of a light pole and utilize an existing AC input to supply power to it. In order to do this, we needed to utilize an articulating boom lift to access the top of the pole as well as modify the pole itself to gain access to the AC power. Unfortunately, this would have caused a safety hazard and would have additional red tape attached to it. This forced us to go a simpler route and design a prototype that could hang off the side of the Jimenez garage. Finally, we ran into a few safety concerns with the large-scale demo that unfortunately did not allow us to operate the unit in a real-world scenario. In order to still showcase the efficacy of the completed demo POM, we instead constructed a small-scale mock-up of the Jimenez flat lot that fits on a regulation-sized tech symposium table.
This slide summarizes how our total cost was divided up.
In the future, this technology could be implemented into a widespread cloud-based ecosystem with a theoretically infinite expandability.
Thank you for listening to our presentation. Before we end this video, we wanted to acknowledge a few people who, without their support, this project would not be possible. Thank you to Dr. Benavides and Dr. Peterson for helping us navigate through this project in both a technical and non-technical perspective. Thank you to David Quensler and Alberto Samaniego for helping us in the manufacturing part of the project. Thank you to Rachel Prince for helping us with media creation and editing. And lastly, thank you to our sponsor, Chad Webster, and the Entrepreneurs Organization for providing us with the funds and business expertise to be able to make the POM a reality. Thanks for watching. Go Runners!